Hi everyone, today we are going to walk you through our project titled A Comparative Study of BiLSTM, TextCN, and DigitalBird for Multi-Class Text Classification. Here is a quick overview of what we will cover today. So let's talk about why we did this. Text classification is one of the core tasks in NLP. It shows up in span filters, support system, sentiment analysis, and name it. The things get tricky with multi-class classification. You have got issues like class imbalance, overlapping semantics, and the need to understand context. Our goal was to compare three models, BiLSTM, TextCN, and DistillBert, under identical settings and see how they stack up in terms of accuracy, efficiency, and interpretability. We built our approach on top of a few keywords. LSTM, of course, has been around for a while and are great at sequence modeling. TextCN is efficient and good at capturing local patterns. And then we have transformers, especially DistillBert, which is a smaller, faster version of BERT. It's pre-trained and widely used in production NLP systems. All three models were trained from scratch using PyTorch, and we keep the settings as fair as possible across the board. So let's starting with the LSTM. The architecture is pretty standard. We use a randomly initialized 200-dimensional binding layer, followed by bidirectional LSTM with 128 hidden units. Each time step combines the forward and backward hidden status. After that, we use a fully connected softmax layer to classify the sentence. Next up, TextCN. Again, we use the same binding layer as BiLSTM. The core idea here is to apply 1D convolution over the sentence using filter of size 3, 4, and 5, each with 100 filters. After roller activation and max pooling, we feed it into a dense layer for classification. It's much faster to train and works surprisingly well for short text. And finally, DistillBert. This one is a pre-trained transformer model. We tokenize the input using word-piece embeddings, and then use the final token representation for classification. A linear layer maps it into 28 lodges. Behind the scenes, it uses multi-head self-attention to learn a contextual relationship between tokens. It's more compute-heavy, but also more powerful. For our experiment, we use a dataset of 30,000 short English sentences. Each one is labeled with a category like UI error or account access. Most sentences are pretty short, 5 to 20 words. We split the dataset into 25,000 for training and 5,000 for testing. The goal is to predict the correct label from 28 options, given just one sentence like this. To compare models fairly, we use standard metrics. Occurrence is how often the model got it right. Precision recall F1 score, all micro averaged to account for class imbalance. Micro-averaging means we treat each class equally, regardless of how often it appears. This is the training configuration of our experiment. So let's look at the results. DistillBert came out on top with 91.1% accuracy and 90.8 F1 score. TextCN was a close second with 89.4% accuracy. BiLSTM lagged slightly behind, score around 87.2% accuracy. Well, TextCN highlights the advantage of contextual embeddings and local feature extraction in multi-class text classification. This table will also test the model's emotion classification tasks inspired by Go Emotions. Again, this Dilbert beats the pack, but we saw the small in performance when compare all models in symbols. So ensembles do help with generalization, especially for underrepresented emotions. This table shows the top 5 performing emotion by F1 score using our symbol model. Gratitude ranks first with an F1 of 0.9. Gratitude ranks first with an F1 of 0.908, followed by amusement, approval, admiration, and excitement. These emotions tend to have clearer expression in text, making them easier to detect. Overall, the result confirms that transformer-based model, especially in symbol, offers strong generalization and robustness in fine-grained emotion classification. This chart shows how each model performs in turn emotion categories. All models do well on a clear emotion like gratitude with F1 score over 0.9, likely due to obvious cues like thank you. But for subtle emotions like approval or annoyance, performance drops, especially for text in and by LSTM. The performance gap is more on clear signal like love and amusement, but grows for subtle ones. So in practice, model choice depends on how fine-grained your emotion detection need to be. We analyze the sample to see how model behave. First, a success case. This Dilbert correct predict UI error while LSTM choose form issue, missing subtle UI cues. Now let's look at the filler case. Text in wrongly picked account access, likely due to keyword matching. This Dilbert got it right again. So overall, this tells us that Dilbert is much better at disambiguating when the sentence is vague or when multi-classes share similar vocabulary. Across all 28 classes, by LSTM tend to over-generalize and miss rare cases. Text-in relies heavy on key overlap but lacks textual understanding. This Dilbert performs best, especially on subtle categories, but needs more compute. So depending on the use case, we might choose differently. If you have sufficient resources like a GPU server, this Dilbert is a great choice. But in resource-constrained environments like mobile or edge devices, text-in could be a practical and efficient alternative. To sum up, this Dilbert gave us the best overall results thanks to its contextual embeddings. Text-in offer a great balance between speed and performance, ideal for deployment with limited compute. Okay, that's all. Thank you for listening.